Let's get started in discussing alkenes and alkynes by taking a look at their structures and physical properties. Both alkenes and alkynes are unsaturated hydrocarbons. In chapter 10, we looked at saturated hydrocarbons, or alkanes and cycloalkanes, and these were molecules that could hold the maximum number of hydrogens per carbon atom. But what we see in alkenes and alkynes is that this is not the case, and we do not have the maximum number of possible hydrogen atoms per carbon atom, and therefore we call these unsaturated hydrocarbons. Another way of thinking about the unsaturation is that in an alkene, we have a carbon-carbon double bond. In fact, that is how we recognize the alkene functional group. And in an alkyne, we have a carbon-carbon triple bond. And when you have a carbon-carbon double or triple bond, this is what we call a unit of unsaturation. So as soon as you see a double or a triple bond in a hydrocarbon, you know that if it's a double bond, of course, it's an alkene. If it's a triple bond, of course, it's an alkyne. But you know that you are dealing with an unsaturated hydrocarbon. The simplest possible alkene is ethene. It has another name, which is ethylene. The ethylene is what we call a common name, and ethene is what we call the IUPAC name. And its molecular formula is C2H4. And the simplest possible alkyne, the IUPAC name for it is ethyne. The common name is acetylene. And if you've ever done any welding before, you may have heard of acetylene gas. And its molecular formula is C2H2. And what you notice right away is that neither of these follow the formula which we saw for alkanes or straight chain alkanes, which was CnH2n plus 2. Neither of these molecular formulas follow that. You can also see that as we go from the alkene to the alkyne, we have less hydrogens per carbon atom. This slide just shows a comparison of alkanes, and this was the focus of chapter 10, was alkanes, and alkenes and alkynes. This is going to be the focus of chapter 11. And in terms of their general formulas, we learned that the general formula for an alkane was CnH2n plus 2. For an alkene, we actually end up losing 2 hydrogen atoms, and that is because of the double bond that's formed, that's highlighted in yellow in the ethylene or ethene molecule that's shown here. So the generic formula, or the general formula for an alkene, is CnH2n. And for an alkyne, since we have a triple bond, we end up losing more than 2 hydrogens. So we end up losing a total of 4 hydrogens compared to an alkane, and thus the generic or general formula is CnH2n minus 2. And here is the structure of ethyne or acetylene right there. So you can see that an alkene, again, possesses the double bond highlighted in yellow, and an alkyne possesses a triple bond. Here are the molecular formulas, and then here are the condensed formulas. Now, we looked at the condensed formulas of alkanes again in chapter 10, but what's important is that when you're writing out the condensed formula for an alkene or an alkyne, we do not leave out a double or triple bond. We have to write that in even in a condensed formula. Remember that condensed formulas, we eliminate carbon-hydrogen single bonds or carbon-carbon single bonds. So we don't eliminate double bonds and we don't eliminate triple bonds in a condensed formula. In alkanes, the central carbon has 4 single bonds, giving it a tetrahedral molecular geometry, and we see that for both carbons in ethane. When carbon is bonded by 1 double bond and 2 single bonds, as in ethene, so both of these carbons that I'm highlighting in red, they both have 2 single bonds and 1 double bond. The molecular geometry about both of those carbons highlighted in red is trigonal planar, because all of the atoms lie in a single plane, so they're all planar or flat. Each bond angle is approximately 120 degrees. When 2 carbon atoms are bonded by a triple bond, as in ethyne, shown over here, each bond angle is 180 degrees. Thus, the molecule is linear and all atoms are positioned in a straight line. And so it's important that you understand that when carbon has 4 single bonds, as in ethane, this carbon that I've highlighted in green, all of the bond angles on that carbon are approximately 109.5 degrees, because the carbon atom has a tetrahedral molecular geometry. In an alkene, like ethene, both of these carbons have a trigonal planar molecular geometry, and all of the bond angles in the molecule are approximately 120 degrees. And when carbon has a triple bond and a single bond, the bond angles are going to be 180 degrees. And that's why ethine has a linear molecular geometry. This slide shows a structural comparison of 5 carbon molecules. We have a 5 carbon alkane, pentane, we have a 5 carbon alkene, 1-pentene, and we have a 5 carbon alkyne, 1-pentyne. It's important that you understand that in the alkane, pentane, each one of these carbons has a tetrahedral molecular geometry because they all have 4 bonds. Every bond angle in that molecule is going to be 109.5 degrees. In the 5 carbon alkene, 1-pentene, in the middle, the carbons that I'm highlighting here in orange, both of those have 2 single bonds and 1 double bond. So both of those carbons highlighted in orange have a trigonal planar molecular geometry. But the remainder of the carbons, which I'm highlighting in red, all have 4 single bonds, and thus those carbons, again, the ones highlighted in red, all are tetrahedral in terms of their molecular geometry, and all have bond angles of 109.5 degrees. Finally, in the 5 carbon alkyne, 1-pentyne, it's important that you understand that the 2 carbons I'm highlighting in blue both have a triple bond and 1 single bond, and thus both of those carbons have a linear molecular geometry. But the remaining 3 carbons all have 4 bonds, and thus they are all tetrahedral, again with that same bond angle of 109.5 degrees. So again, when a carbon is trigonal planar, all the bond angles are 120 degrees, and when a carbon atom has a linear molecular geometry, the bond angle is 180 degrees. This slide just draws our attention to something that I spoke about earlier in this video, is that multiple bonds are always drawn in condensed structures. So it's important that you understand that when we're drawing a condensed structure, say we want to draw a condensed structure of this molecule, remember, condensed structures only eliminate carbon-carbon and carbon-hydrogen single bonds. Therefore, we have to keep that double bond. And that's why in this structure here, it is the same as the structure on the far left, but we have to keep that double bond. The same thing applies with alkyne. So if we take a look at this alkyne here, if I want to draw the condensed structure of that alkyne, the only bonds I can eliminate or omit are the single bonds that I have highlighted in red. I have to keep the triple bond. So just highlighting that you have to always keep double and triple bonds when you're writing condensed structures. Just like we saw for alkanes, the melting points and boiling points for alkenes and alkynes are the result of London dispersion forces. These are the types of intermolecular forces that are experienced by nonpolar molecules, which hydrocarbons are. London forces, or the intermolecular forces in hydrocarbons, increase as the molar mass of the molecule and the number of electrons increase. Thus, the London dispersion forces are stronger and the attraction is greater for molecules having a larger surface area. We can predict that longer, higher molar mass alkenes and alkynes are going to exhibit stronger London dispersion forces and therefore have higher boiling and melting points. The melting points and boiling points of several alkenes and alkynes are shown in this table, and they reveal that this prediction is true. If we just do a quick comparison of ethene, which I have highlighted in yellow, which has a boiling point of 103.7 degrees, you can see that as I go from ethene to propene to 1-butene, all we're doing is we're adding carbons to the structural formula or to the molecular formula, either way. And you can see that what's happening is that the boiling point is increasing. Thus, based off of these 3 compounds I have highlighted in blue, we can clearly see that boiling points rise with molecular weight. Alkenes, alkynes, and aromatic compounds are less dense than water and are nonpolar. Since they are nonpolar, the like dissolves like rule tells us that they're not going to be soluble in water. Just like alkanes, they're going to be very soluble in nonpolar solvents like other hydrocarbons.